Hello. Today, in this video, I'd like to talk to you about two of the most important quantities when it comes to talking about electricity and electrical circuits, and that's potential and current. We're going to split this up into two segments. First, we're going to talk about potential and how it relates to work and energy. It's kind of a fundamental building block of how electrical circuits work. Then we're going to finally define what electrical current is, talk about how it flows, and finally see some examples of how to calculate current flowing through a circuit. To get us started off, I'd like us to consider a thought problem here in this first page. Over here we have a positive sphere, and next to it I have 2 points, B and A. And I want you to imagine what would happen if you tried to place a positive charge over here at B and move that positive charge toward A. Think about taking two north poles of a magnet and pushing them together. Well, we know two like charges are going to repel, and so that movement would require energy, require or take energy. And we know whenever something takes energy, that also requires work. So that movement would require energy and thus require work. Now, that kind of an energy has a name, and that name we give that is electrical potential energy. And this is different what we've been talking about before. Before we've been dealing with electrostatics, having charges just in one single place, transferring them and thinking about them after they've moved. But now we're going to start thinking about what happens when charges do move, and how do we explain and talk about that movement. And the way we do that is talking about electrical potential energy. But energy is a little messy to deal with, and so physicists have come up with a different way of talking about potential energy, and that's with electrical potential. So a formal definition of electrical potential says that electric potential difference, which is V, measures the amount of energy that is absorbed or released in moving a charge across a difference in an electric field. So if I have an electric field between 2 points, let's say I've got a positive plate there and a negative plate there, we know that the field lines would point this way from that positive plate to that negative plate. Well, a potential difference is the amount of energy that we would get when we move from this plate down to that plate, when we move that charge through that field. So we know that charge is moving, gives us energy, and that energy is related to potential difference. This helps explain, for example, why charges flow like an electrical circuit. If I have an electrical circuit, I have a positive high potential over here and a negative low potential. Those charges are going to flow through my electrical circuit and thus power my light because they release energy flowing from high potential to low potential. So it's that potential difference between two different places that provides a circuit. That's also why voltage or electrical potential is dangerous, because there's a lot of energy that can be stored in electrical charges. If I have a place like a battery or like some type of an electrified wire that has a lot of charges there, those charges don't want to be near other charges. They want to spread out. And if you provide a path, an easy path to the ground by touching an electrical fence or something like that, they will flow through you and release energy as they're doing so. And it's that energy that's ultimately dangerous. So electrical potential difference measures the energy contained in a certain place that can be dissipated by moving that charge to that field. Now, mathematically, we can represent that with an equation. And our equation for our electric potential difference, V, is going to be W divided by Q. Now, let's define our terms here. W, like we've seen before, is also called work. But we have to be careful, because you've noticed when we're talking about electrical potentials and electrical energy, we've been using work and electrical energy interchangeably. And that's going to be true here. So W is work, which is the same thing as electrical energy. So it's okay to use either of those terms to mean the same thing. So W here is work and electrical energy. And then Q, like we've seen before, just means charge. Let's think about units for a second. We know that work and electrical energy are measured in joules, charge is measured in coulombs, and so it looks like my unit for V, my electrical potential difference, would end up being joules per coulomb. We give that a name, and the name for a joule per coulomb is a volt, a V. Now, I'd like to talk about one thing before we move on here. We sometimes use the synonym voltage to mean electrical potential difference, but I want you to be careful with that, because voltage is also the unit that electrical potential is measured in. When I say something has 12 volts, that tells me that the electrical potential difference from that thing to a standard, like the ground, is measured as 12 volts, but it doesn't mean that voltage is anything by itself. So we want to be careful to make sure that we know the unit is volts, but the quantity we're measuring is electrical potential difference. Okay, let's take a look and see some examples of how this would be calculated. So for example, if 60 joules of work is required to move 5 coulombs of charge between 2 points in an electric field, what's the potential difference between these 2 points? So if I have 1 point here and 1 point there, moving that charge from one place to another requires 60 joules. Well, I set up my equation. I know that electrical potential difference, V, is W divided by Q. I plug in my numbers, 60 joules divided by 5 coulombs, and I end up getting 12 joules per coulomb, which is also the same as 12 volts, like a 12-volt battery here. In our second example, we're going to flip it up a little bit. We say that the potential difference now is 10 volts, and that's between 2 points A and B within an electric field. They now want to know what's the charge that requires 2 times 10 to the minus second joules of work to move from A to B. Once again, we use the same equation, V equals W divided by Q. Now I'm plugging in the 10 volts as my electrical potential difference. My electrical energy, or work, is 2 times 10 to the minus second joules, and I'm solving for Q here. Here, you probably were going to go ahead and cross multiply. So 10 times Q equals 2 times 10 to the minus second, divide by the 10. If you solve this in your calculator, you're going to end up with a Q equal to 2 times 10 to the minus third coulombs. So that's how to calculate electric potential difference. But there's a few other ways we're going to see it come up in this course. One other way is that we deal with charges often that are really small. Over in our example problems, we had charges that were, tens of coulombs or a tenth or a thousandth of a coulomb. But an electron, remember, one electron in our elementary charge is negative 1.6 times 10 to the minus 19th coulombs. That's really, really tiny compared to those numbers we were seeing before. And so physicists often use a different unit to represent really small amounts of energy that are used to take an electron, for example, across some type of voltage. So to represent small amounts of work or energy, the unit we're going to use is called the electron volt, or EV. And it's the amount of work done moving an elementary charge, like an electron or a proton, through a potential difference of 1 volt, hence why it's called an electron volt. So for example, if you look at this picture down here, this is the kind of situation you'd see an electron volt in. If I have a battery here that's applying 1 volt, and 1 electron moves from this plate to that plate, the amount of energy that is gained by that electron moving from there to there is 1 electron volt. We can see here why this kind of analysis is so different than what we've seen before. We're always talking about things moving. We're thinking about the process of charges moving from one place to another, the energy that's required to do that, and ultimately the potential that it can have from going there. So in our example problem, we now have a proton that's moved through a potential difference of 10 volts in an electric field. We want to know how much work in electron volts is required to move this proton. Well, similar to what we've done before, we know that our electric potential difference, V, is equal to work divided by Q. I plug in my 10 volts as my electric potential difference. We want to find the work, but now I have to put in my Q. Now this is for a proton, and I want this in electron volts, so we're not going to use the 1.6 times 10 to the minus 19th. Instead, we have to remember that a proton has the same charge as an electron, so it is also one elementary charge. So I plug in 1e here as my charge. Solve this out, W, or my work or electrical energy, is equal to 1e times 10 volts, which is equal to 1 times 10, 10 electron volts. So you can see this unit just works out naturally. 1 proton through 10 volts gives me 10 electron volts. Now, there's one more special situation we're going to see before we move on to talk about current. And that special situation involves parallel plates. Physicists love parallel plates. Why? Because they're super easy to understand and see. And the reason why they're super easy to understand and visualize is because between a pair of charged parallel plates, the electric field E is a constant. It's easy to see why. If you think about a positive plate that runs forever this way and a negative plate that runs forever this way, then the field lines between those plates always point down. And if those plates are the same distance away, that runs on forever, that E is always constant. And so this is one of the best ways for physicists to make a constant electric field, which are useful for many of our devices we use today. Now, when you're going to make a parallel plate device, whether it's a capacitor or something else you're going to use, that electrical potential difference between the plates, which that represents how much energy you can get out of a charge, depends on two things. It depends on the electric field, and it depends on the charge that you're moving between the plates. Now, mathematically, we can think about that by thinking about the work done on a charge that's placed between these two fields. So I'm going to go ahead and pretend we place a positive charge at the top of this plate, and we move it down toward the negative plate. It's going to be attracted there because of that field line. So if we define a distance between those two plates, we can say that the electrical potential is just the work divided by the charge. Well, the work done here would just be equal to the force on that charge times the distance, because work is force times distance. And the force that we're using here is the electrical force, the electrostatic force. And that's going to be divided by Q. Now, we already know what Fe divided by Q is. Fe divided by Q is equal to E. And so if I solve this out, V is equal to Fe divided by Q, which is E times D, our distance. So voltage is going to be equal to E times D. Okay, moving on here. Let's go ahead and talk now about the flow of charges in a circuit, otherwise known as the electrical current. So electrical current is the flow of positive charges from high potential to low potential in a circuit, just like you can think of a river, where water in a river will flow down that river from a high elevation to a low elevation. Current will also flow from a higher quote-unquote voltage, or what we know as electrical potential difference, to a low voltage or a low electrical potential difference. So electrical charges flow from high to low. But we have to be careful, because what's actually moving in a wire to create electricity? Well, it's in the name. Electricity must be talking about flowing electrons. And electrons don't flow the same way as current, because current is the flow of positive charges from high to low potential. Positive charges go from high to low. And so current flow is from high to low potential. But I don't want you ever to forget that electrons actually go the other way. Electrons are going to flow from low to high potential. And if you want to think about low as negative and high as positive, this makes sense. Electrons are going to flow from low, negative, to high, positive. They're attracted to a more positive location, and that more positive location is going to have a higher electrical potential. The reason why this is all backwards is due to some historical stuff, and people often try to blame Ben Franklin. I don't want to give him too hard of a time. Ben Franklin was a pretty cool guy, but if you want to go look that up. It's kind of an interesting story to try to figure out why electrons actually flow the opposite way that current does in a circuit. Let's take a look at some examples of this then. Here, I want to talk about it mathematically first. So mathematically, current, which we represent using the letter I, that's current, we're going to say that's equal to the change in Q divided by time. Now we've already seen Q before. Q is charge, and T is our time. And don't forget, change or delta always means final minus initial. So it'd be our final charge minus our initial charge divided by the time. For example, I have a charge of 30 coulombs that passes through a 24 ohm resistor in 6 seconds. What's the current through the resistor? Well, don't let yourself get confused. We haven't talked about this yet. 24 ohms? What's that mean? They often throw information in a problem you do not need. We know the charge that passes, and we know the time. We can use our equation to find the current. Our current, I, is going to be equal to 30 coulombs divided by 6 seconds. 30 divided by 6, that's going to give me 5. Now, we haven't talked about the unit of current yet, but it looks like just dividing coulombs divided by seconds, I get coulombs per second, which is a perfectly fine unit, and you're more than welcome to use that. We give that a name, though. Current is measured in coulombs divided by seconds, and the name for that is an ampere, otherwise known as an amp. We can also abbreviate that for another type of bracket as A. So 5 coulombs or 5 amps. Now, once again, it can be tempting to call current amperage, and oftentimes you'll hear it worked out that way. But just like with voltage and electrical potential difference, be careful that you don't replace the idea of what current is with the unit amp or amperage. Current is the flow of electrons, as amp or amperage is what we measure current in. One final example, we want to have a light bulb. This light bulb draws a current of 2 amps. We want to know how many coulombs of electric charge pass through this light bulb in 1 minute. Well, I know that my current, is equal to delta Q divided by T. I know my I is 2.0 amps. Delta Q is what we're looking for, and my time, remember that amps is per second, I should turn this time, 1 minute, into seconds. So I'm going to turn that into 60 seconds, multiplying those out. The amount of coulombs that will pass there, 60 times 2, or 120 coulombs. Okay, well today we've talked about 2 really important concepts. Electrical potential difference, which is the amount of energy gained or released when a charge is moved through an electric field, and current, the flow of electrons through a circuit or some other device that is measured in coulombs per second or amps. Don't forget that electron flow is the opposite of current flow, that current is the movement of positive charges while electrons are negative. And finally, don't forget to make sure you separate your units, like amps or voltage, from the actual concept, electrical potential difference or current.